Welcome back to integration. In the last lesson, we looked at areas enclosed by the x-axis, but now we are going to flip things around and look at areas enclosed by the y-axis. So if we have some curve, y equals f of x, and we wanted to find an area that is bounded by the curve and the y-axis, it might look a little something like this. Notice that we still have our lower and upper bounds of a and b, but because they're on the y-axis, they are y equals a and y equals b. Now another change for us, because everything is flipped around from what we have been doing previously, that means we need to flip our function around. So how we express this algebraically, we no longer want to express it as y equals f of x, but rather x equals f of y. Now we've also seen previously that when we are looking at areas enclosed by the x-axis, areas above the x-axis have a positive definite integral, and areas below the x-axis have a negative definite integral. Well, the same kind of thing happens here. An area such as this one, which is to the right of the y-axis, will give a positive definite integral. Whereas if we're looking at an area like this, which is located to the left of the y-axis, then we will get a negative definite integral. So let's take this information and have a go at a few examples now. Example 1. Find the area enclosed by the curve x equals y squared, the y-axis, and the lines y equals 1 and y equals 3. So we can see here it's an area enclosed by the curve and the y-axis problem, which means we want to express our function in the form x is a function of y. But notice for this particular question, that's how it's been given to us. X is a function of y. So that's really good for us. We're also given the lines y equals 1 and y equals 3. These are both horizontal lines. So let's graph this to have a little bit of an idea of what's going on, and then we will solve. But what does this graph actually look like? This isn't something that we see very often, but you might notice it looks a little something like y equals x squared. And we know that y equals x squared is just our standard parabola. So the act of swapping the x and the y values just means that our normal looking parabola is going to flip or swap onto its side. So let's draw that in. And then we also want our horizontal lines of y equals 1 and y equals 3. And so now we can see the area that has been enclosed. Now, just quickly before we get on to the integration, do you know what this x value would be and what this x value would be? Well, because the function is in the form x equals y squared, we can simply substitute in the y values 1 and 3 and get our x values. So 1 squared gives us 1, and y equals 3, well, 3 squared gives us 9. And so while these values are not necessary for this question in particular, this idea of being able to find corresponding x and y values can come in handy for these types of problems. Alrighty, so let's find this area. Now, because it's on the right-hand side of the y-axis, we can just go straight to finding the definite integral, because it will give us a positive value. Now, it's between the limits of 1 and 3, and our function is y squared. So this means that we are integrating with respect to y. So rather than dx, we have dy. But everything still works the same. While we're used to doing something more like x squared dx, and now we're doing y squared dy, it's just a change of variable. So in terms of the actual algorithms that we use, the processes, they remain the same. So if you had to integrate y squared, well, you would raise the power by 1 and put it over that new power. And that's it. Because our lower and upper bounds are already in terms of y, we can substitute them in using the fundamental theorem of calculus. And so we get 3 cubed on 3 minus 1 cubed on 3. 3 cubed is 27 and 1 cubed is 1. So 27 minus 1 gives us 26 over 3. And if we wanted to express that as a mixed number, we get 8 and 2/3. And that's our answer. Because it's an area, we put square units and we're done. Now on to example 2. Find the area enclosed by the curve y equals x squared. Alright, so our standard parabola, the y-axis, and the line y equals 4 in the first quadrant. Alright, so what's going on here? Let's draw our diagram. We've got the standard parabola. We know its vertex is at the origin, but we also need to put in the line y equals 4. And when we do that, we see that it hits the curve at 2 points. So this is where the first quadrant information comes in. We just want the area that is between the y-axis, the curve, and the line y equals 4 in this first quadrant here, not over here. And so there we go. There's the area that we're after. For this example, I'd like to do 2 methods. Okay, now you might find one method better than the other, okay, but I'm going to show you both so that you have a more well-rounded understanding of what's going on. So to start with, let's follow the same kind of method as what we saw in the first example. Because it's an area enclosed by the curve and the y-axis, we want our function as a function of y. And we haven't quite got that at the moment. So let's rearrange our y equals x squared, or x squared equals y, so that we make x the subject. We need to take the square root of both sides, and when we do that, we end up with plus or minus the square root of y. This is actually 2 different sections of our parabola. The positive square root is this section over here, and the negative square root is over here to the left. Because we're just interested in the section on the right, we are just going to take x to be the positive square root of y. And so now we have our function in the form x equals a function of y. Now remember as well, we might just add this in here, that the square root of y is y to the half. So let's go ahead and integrate, keeping in mind that because the area is to the right, we are going to get a positive definite integral. So we can just go straight ahead. We don't have to worry about any absolute value signs. So the area is given by the integral between 0 along here and 4 here of the function y equals y to the power of a half, dy. Raising the power by 1. So y to the power of a half, when we plus 1, that takes us up to 3 on 2, over that power of 3 on 2. And with 4 and 0, this gives us, and remember fractions within fractions, okay, we can change that around a little bit. So we get 2y to the power of 3 on 2 over 3. Now hopefully you can see that when we substitute in 0, the whole thing will be 0. So really we are just after what we get when we substitute in 4. When we evaluate this, oh, sorry, my bad with the 2 there, it should be a 3. When we evaluate this, you can plug it into your calculator, or you can think, all right, square root of 4, that's 2. 2 cubed, that's 8. And so we get 2 lots of 8, which is 16 over 3. Or, as a mixed, that's 5 and 1/3. Okay, square units. So that's one way of doing it. However, I would like you to consider a second method. So let's go back to our original diagram. Notice that when we are after this area here, what we have done previously is find the area between curves and the x-axis, so this area here. And given that our function was originally stated as y equals x squared, this green area probably would have been easier for us to find. Notice that the combination of the green area and the red area is just a rectangle. So we could find the area of the whole thing, the rectangle, and subtract the green area, and that would leave us with the area we are after. The only question is, what is this x value here? Well, because we know that this is y equals 4, what x value squares to give 4? Well, that's 2. So the area of the rectangle is simply the base times the height, which is 8 square units. And then the green area, which we'll call area 1, is the area under the curve but above the x-axis. So we can evaluate that like we've seen in previous lessons. The integral of x squared between 2 and 0. Integrating x squared, we get x cubed on 3. And when we throw in our values, we get 2 cubed, which is 8, and 0. So the overall area that we are after is the area of the rectangle minus this area 1 that we've just found. 8 minus 8/3 gives us the exact same thing as what we got by the first method, 5 and 1/3. So both methods are perfectly fine, and it's just good to see both ways of doing it, because sometimes it's going to be easier to integrate between the curve and the x-axis, or maybe it'll be easier to integrate between the curve and the y-axis. Okay, so it's good to know that in either case, we can just set up a rectangle for the total area, and then we can play around with the two areas that make up that rectangle. Okay, one more example. Find the area enclosed between the curve y equals the square root of x plus 1, the y-axis, and the lines y equals 0 and y equals 3. So once again, because we are finding the area between a curve and the y-axis, we want our equation or our function in the form x equals f of y. But at the moment it's in the standard form, y equals f of x, so let's change that around. Okay, so the square root of x plus 1 is equal to y, just swapping it around. Let's square both sides to get rid of that square root. And then we will subtract 1. So x equals y squared minus 1. Now, in a very similar way to what we did at the start of this video with the first example, notice that x equals y squared minus 1 is, it looks like y equals x squared minus 1. So that's a parabola moved down 1. Well, it's just turned on its side now. So this is minus 1 here at its vertex. And then hopefully you can see, okay, we've got when x equals 0, if you go back to the original function, we've got the square root of 1. Okay, so this up here, and then this would be minus 1. But this is the full parabola, right? The original function we were given is just the positive square root, right? Like technically what we've got here is called a relation. Okay, we've just got the positive square root. So we actually don't want this bottom half. And then the last thing to do is to add in our horizontal lines. Now y equals 0, that's just the x-axis, so that's already there. And then y equals 3. Not particularly to scale, but it's just a sketch. All right, so we've got two parts to our area. The first part here on the left, which we will label as area 1. Now we've got to remember that because this is to the left of the y-axis, we are going to get a negative definite integral. And then we have the second part, which we'll call area 2. This will give us a positive definite integral. Our total area is just going to be the sum of those two. Okay, let's start with area 1. So we are going from y equals 0 to y equals 1. Now, because it's going to be negative, let's throw in our absolute value signs. And our function is y squared minus 1 with respect to y. Integrating, we get y cubed on 3 minus y. That's between 1 and 0. And then when we evaluate, we see that we get 1 cubed over 3, so that's 1/3, minus 1. Now, we also will have minus whatever we get when we substitute in 0, but that's just 0. Now, 1/3 minus 1, that's negative 2/3. But because we have the absolute value signs around the outside, that turns our area into positive 2/3. Now perhaps you can see here why I'm actually a fan of just working out the integral, calling it I, and then applying the absolute value sign at the very end. Just saves putting the absolute value sign over and over again. All right, so there's area 1. Let's go back up and work out area 2. Now area 2, it's the same function, but our limits are between 1, y equals 1, and y equals 3. Now this one we don't have to worry about the absolute value signs because we know our answer will be positive. Applying the same integration as before, which is nice. Let's see what we get. So 3 cubed on 3 minus 3. That's the first bit. Then we've got to take away our 1 cubed, which is just 1, on 3 minus 1. Three cubed is 27, and 27 divided by 3 is 9. So we get 9 minus 3 in the first brackets, and then, well, we already know that this is negative 2/3 because we just did it before. And so 9 minus 3 is 6 plus this 2/3, so 6 2/3. Now these are our two individual areas, but of course we are after the total area. So the total area is the sum of A1 and A2, which is 2/3 plus 6 2/3. And so that gives us a final answer of 7 1/3. And there we have it. All right, great job everyone.